Once upon a time, there was a game called Crysis.
Maximum speed. Maximum strength.
Yeah, so it was very successful and they sold a zillion copies and made a lot of money and of course released a whole series of sequels. But the main thing for us here is the list of rendering techniques implemented by the developers. Things like advanced shadow mapping, water rendering, volumetric fog, and many more. Today we will take a look at one of these techniques, Screen Space Ambient Occlusion or SSAO. We all know what ambient lighting is, right? It is a type of light which is omnipresent, omnidirectional, and has a fixed intensity on every object in the scene. It is also the simplest light type to calculate and it helps us avoid completely dark objects due to distance from other light sources as well as other issues. But it's also too simple and not enough realistic. We can improve it using ambient occlusion, where we calculate how exposed the pixel is to the close vicinity around it. For example, we expect a corner to be less exposed to light than the walls around it and therefore to reflect less ambient light. The best way to calculate ambient occlusion is probably using ray tracing, but it wasn't available for real-time 3D games back in 2007 when Crysis was released. Even today you need a high-end GPU to make use of it. So Vladimir Kajalin, one of the developers over at Crytek, came up with the idea to approximate ambient occlusion in screen space by calculating it once per pixel. This worked very well and was one of the major improvements in the Crysis engine. It was also adopted by major game engines such as Unity, Unreal, and Frostbite. In the following years, SSAO was improved by various techniques such as HBAO, GTAO, RTAO, and GMC BMW VO. Okay, the last one was a joke, of course. But anyway, the implementation that we're going to see today is from the first edition of the 3D Graphics Rendering Cookbook. This book provides implementations for OpenGL and Vulkan. We will study the OpenGL version, which will make it very easy later on to port it to Vulkan. I've also added a few improvements which I found online. Okay, let's get into it. To implement SSAO, we are going to create an occlusion texture, which represents how exposed or hidden each pixel is. This is basically the ambient occlusion that we talked about. The reason this technique is considered to be screen space is that instead of going over the entire surface of the object at some intervals, we do the ambient occlusion calculation after the scene has already been rendered. So we have a populated color and depth buffers as input. The color buffer contains the colors of the closest pixels, and the depth buffer contains the depth of these pixels. This means we have a fixed overhead for the SSAO calculation, regardless the complexity of the 3D scene. In practice, instead of rendering the scene directly into the back buffer of the default frame buffer to be displayed in the window, we will render it into a user-defined frame buffer. This is similar to what we did in shadow mapping, but this frame buffer will include both the depth buffer and the color buffer. After rendering into this new frame buffer, we will do an SSAO pass, where the depth buffer will be used to calculate the SSAO factor for every pixel. Finally, a combined pass will read the color buffer and the SSAO buffer, and will use the occlusion factor to tune down the intensity of every pixel. In general, to calculate the occlusion factor of a given surface point, we need to sample several points around it. As you can see, depending on the geometry of the surface, some of the points are above the surface and some of them are buried inside it. The occlusion factor is the ratio between the number of points inside the surface and the total number of sample points. The more points inside the surface, the more occluded the surface point is. We can calculate the accurate occlusion factor by tracing rays from the surface point to each of the sample points. If the ray crosses the surface, the sample point contributes to the occlusion factor. But this is way too expensive. Instead, we are going to compare the Z value in the depth buffer between the surface point and each sample point. If the sample point is above the surface, we will sample the depth of the closest point on the surface along the ray from the camera to the sample point. If the sample point is inside the surface, the same thing will happen. So we basically end up comparing the Z value of 2 points on the surface. If the Z value of the main surface point is larger than that of the sample point, we assume the surface point is occluded with respect to the sample point. This will happen, for example, when the surface point is in some sort of a cavity. But if the surface point is on the edge of a wall, then most likely its Z value will be smaller than most of the sample points around it. Basing the calculation of ambient occlusion on the depth buffer is not always accurate, but in most cases it is good enough and is fairly inexpensive to calculate in real time. So this is the theory, and now let's dive into the implementation. If for some reason you are already rendering your scene into a user-defined frame buffer, then you're good to go. But if not, you can use my frame buffer class as a reference for that. The class maintains the width and height of the frame buffer, as well as handles for the FBO and the color and depth buffers. The class supports both direct state access or DSA, as well as non-DSA functions, depending on the opengl version you have on your system. Let's assume that you have a fairly modern version of the API, so DSA. In general, you need to create the handle of the FBO, then the color buffer and potentially the depth buffer. Then you need to attach them to the FBO by calling GL-named frame buffer texture on the corresponding bind point. Finally, we need to set the first color attachment as both the input and output targets of the frame buffer, because we are going to render into it and also read from it. Always remember to check the frame buffer status before you start using it, because it may help you trap some nasty bugs. For the depth buffer, we need to create a 2D texture handle, allocate the storage for a 32-bit floating point depth component, and set the minification and magnification filter to linear, the base MIP map level to 0, and the wrapping modes to clamp to edge. The non-DSA version is below, and it is very similar. The color buffer is mostly the same as the depth buffer, except for the internal format. Right now the class supports a limited set of formats based on the requested number of components. I will probably expand this in the future as soon as it is needed. The class also provides a few helper functions for binding the FBO for writing and reading, as well as clearing. You can take a closer look at these later on. Once the frame buffer class is working correctly, you need to initialize it and bind it for writing at the beginning of your main lighting pass. The problem is that doing just that will give you a boring empty window. We need to copy from the user FBO to the default FBO. There are at least 2 ways to do that. You can render a full screen quad to copy between the FBOs pixel by pixel. If you're interested in that, you can use my code here as a reference. But opengl provides a better way to blit one FBO to another in a single function call. This should work faster than the shader method. The frame buffer class provides a wrapper function for that. At this point, the scene should look as usual. The next step is to add an SSAO pass after the main lighting pass. For this pass, we need another FBO for storing the per pixel occlusion factor. As you can see, I've created this FBO with 3 components, so when IMGUI renders this buffer, it is shown in grayscale. All 3 components contain the factor. In a production system, we only need a single component, so much less memory. Just bear in mind that by default, IMGUI will render it in red in this case. Back to the application code. Since this is a screen space technique, we can disable the depth test because we are not rendering the regular geometry. The parameters for the shader are provided in a uniform buffer object, so we update the contents and bind the UBO to the shader. In addition, the shader needs 3 textures as input: the depth buffer from the lighting pass, a normal map which contains the normal for every pixel, and a rotation texture. I'll talk more about these textures when they are actually used. We can now enable the SSAO technique and call render, which calls GLDraw arrays for 6 vertices. Before leaving this function, we have to re-enable the depth test. Now let's take a look at the vertex shader. This is a standard screen space vertex shader. The 6 vertices create 2 triangles which span the entire NDC space from -1, -1 in the bottom left corner to 1, 1 in the top right. We used GLVertex ID to fetch the next vertex from the array. The texture coordinates are calculated by converting the NDC space to texture space, which is 0 to 1. Using a static vertex array in the shader is very handy, because this means we don't actually need any vertex or index buffers, and we can reuse this shader for every screen space technique. We can now take a look at the fragment shader. This shader contains a 3D array of random sample points. I've created the array using the following function and simply copied its output into the shader. Some people like to generate the sample points during runtime and load them into a buffer, but I think that for this tutorial this is good enough. We use the standard C++ library to generate random values between 0 and 1. The x and y are mapped to the range of -1 to 1, and z stays between 0 and 1. This is because the sample points exist in tangent space, where the z component points out of the surface, like a normal vector, so we don't need any negative values for it. But a uniform distribution will result in a flat look, and sampling too far from the main surface point is a waste of performance. Therefore, we prefer to cluster most of the sample points around the origin. So we create a linear curve along the sample array, and we raise it to the power of 2 to turn it into a quadratic curve. We use this curve to interpolate between point 1 and 1. The result, of course, will be biased towards the lower value. We can now use it to scale the sample point and bring it closer to the origin. We start the fragment shader by sampling the depth buffer and linearizing the result back to view space. Why can't we simply do the comparison using the original non-linear value? As you probably know, most of the values in the depth buffer are concentrated near 0. This means that if we have a wall close to the end of the frostum, the depth buffer will see it as almost 1, whereas a wall around the center of the frostum will also be almost 1, but the difference is enough to produce a correct depth test result. For SSAO, this is simply not good enough. We have to do the comparison using the view space Z to avoid anomalies such as bending and popping. Reconstructing Z from the depth buffer may seem like a daunting task, so just remember that we multiply the view space position by the projection matrix, which means that Z is multiplied by this value, denoted A, and we add this guy, denoted B. Then perspective division takes place, so we divide everything by W, which contains Z. And finally, we map the NDC coordinates to the 0 to 1 range to be stored in the depth buffer. To summarize, NDC Z is calculated as follows. In a series of simple steps, we can reconstruct the original Z. Take a few minutes to review these steps. Okay, so the following function does it in GLSL code. At this point, you should definitely try to visualize the view space Z to make sure it's correct. But this value is probably much more than 1, so we divide it by the far Z to normalize it as a color. As you can see, Linear Z provides a much nicer look of the depth buffer. Okay, let's continue. The next step is to orient our kernel of sample points around the current pixel. Remember that the x and y of the sample points go from -1 to 1, and z is 0 to 1, making it a hemisphere. But we can't use it as is, because it's kind of standing upright, whereas the surface can be oriented in different ways. If the hemisphere always points in the same direction, the occlusion will seem to be detached from the actual geometry. For example, the floor here is getting some occlusion, where it shouldn't, whereas the wall in the back is not. We expect both elements to have the same level of occlusion. To make a long story short, we need to rotate the hemisphere and make it align with the surface normal. But even if we do that, there are still a million ways in which the hemisphere can be rotated on top of the surface. Which direction should we choose? In such cases, the common practice is to go with some random value. Therefore, we will use a random texture. Surprisingly, even a 4x4 texture should be good enough for most cases. We can visualize this texture as follows, but remember that essentially, each texel is just a random vector. This is the second texture which is bound in the SSAO pass. We need to do some thinking about how to sample from this texture. If we simply use the same texture coordinates that we used for sampling the depth buffer, those 4x4 texels will be stretched all over the output frame buffer, and it will not be very random, even considering interpolation. We prefer tiling the random texture over the entire window. We do that by scaling the texture coordinates up to the ratio between the dimensions of the output frame buffer and the random texture. For example, if the output is 1000 by 1000, we need to scale the texture coordinates by 250 so that the random texture will be tiled 250 times across U and V. We can now sample a random vector from the texture. Next, we sample a normal from the normal map. If you have a deferred rendering pipeline, then you have a G buffer with a dedicated texture for each vertex attribute, position, texture coordinates, normal, and etc. So I'm referring to the normal map from the G buffer. Since I'm not doing deferred rendering, I had to add a normal pass which only transforms the normal vector and writes it out to its own frame buffer. After the normal pass, this frame buffer contains the normal vectors of the closest pixels, so we can sample from it using the same texture coordinates as we did for sampling the depth buffer. We can now use the Gram-Schmidt process to create an orthonormal basis for the current surface point. From the normal vector and the random vector, we calculate a tangent vector. A cross product between the normal and tangent provides the bitangent. In the normal pass, we transform the normals into view space, so the vector basis that we create from the normal, tangent, and bitangent transforms from tangent space to view space. We can now go over the array of sample points and transform the vectors to view space. What we do next is to add a view space vector to the texture coordinate. This may seem wrong because one value is in screen space and the other is in view space. But notice that we also divide the view space vector by the linear Z. This kind of projects the view space vector to the screen. This means that the hemisphere of sample points will be smaller for more distant pixels and larger for the pixels close to the camera. This makes sense from a perspective projection point of view. Also remember that for small displacements near a given fragment, the mapping from view space to screen space is approximately linear, which makes this calculation approximately correct. Again, good enough. Also notice the radius parameter here, which allows the user to tune the size of the hemisphere. Next, we clamp the result of the previous stage. To make it a legit texture coordinate, we sample the corresponding value from the depth buffer and we linearize it back to Z in view space. We can now subtract this linear Z from the original. If the result is positive, it means that this sample point contributes to the overall occlusion. If not, the contribution is 0. Using this result, we calculate the occlusion as a bell-shaped curve, which favors the mid-range occluders and reduces the effect of very close or very distant ones. We also make sure not to get negative results here. Again, we have a user-tunable variable to play with this curve. At the end of the loop, we accumulate the occlusion into an attenuation parameter. But instead of doing it using the original value, we apply a smooth, nonlinear attenuation function. First of all, we raise the occlusion to the power of 2. This increases the difference between strong and weak occlusion. We add 1 in the denominator to avoid a division by 0 and to normalize the result. And finally, we take the reciprocal, which makes it into a smooth, inverse attenuation function. We are now almost at the end of the shader. After accumulating the contribution from all sample points, we divide by 64 to get the average, and we clamp it one last time between 0 and 1 to avoid radical changes to the intensity of the pixel color. One final user-tunable parameter is here to allow us to scale the result. The SSAO pass is finally complete, and the last render pass is the SSAO combine pass, where we combine the occlusion factor from the SSAO pass and the color buffer from the main lighting pass. We start by binding the default frame buffer for writing. We actually don't need to clear it because we're going to use the same full screen quad vertex shader from the SSAO render pass. We bind the lighting FBO and the SSAO FBO for reading and render the quad. In the fragment shader, we just need to sample the color and the corresponding SSAO factor. Instead of simply multiplying the factor by the color, we provide two user variables: a bias to adjust the factor and a scale to interpolate between the original color and the color after applying the ambient occlusion. All the variables that we have discussed are available in the GUI of this demo. And this is basically it. There are many variations to this technique as well as improvements by various people over the years. For example, if you look closely, you can see that the SSAO buffer is not entirely smooth. It's a common practice to apply a blur shader here to take care of that, which is probably what we're going to do in the next tutorial. So let me know in the comments what you think. Thank you for watching, and I will see you next time.
Maximum